Fine. Hi. So I'm the CTO of Golem. I'm going to give you a brief recap of where we are now in terms of SGX, SGX-related technologies, the development, and shortly about the future of our development and how we foresee SGX developing in the community and for our project. So, just a short recap. SGX stands for Software Guard Extensions. This is extensions from Intel, and this technology is in principle used to guard the software and the data from the hardware, especially the enclave, the container in which the software is run, from the host on which it is run. So you don't have to trust the host. You just have to trust the CPU, and only CPU in here. And once the enclave is set, which is good, we need to make sure that this is the right enclave and that the host hosting it is not tampering with it and is not simulating the enclave. So we need to do some sort of verification that the enclave run on the host, which may be malicious, is really the right enclave and is going to compute what we would like it to compute. So there is a process called remote attestation, which is used exactly for this purpose, to make sure that the enclave in question is the valid one and it is not simulated by the host. This process is relatively straightforward, but there are quite a few misconceptions regarding, especially regarding Intel attestation service. There are one on the left, and I'd like to recap it shortly. So once enclave is run, a report called quote is generated. This report contains a few important fields, especially the payload and the enclave hash. So it identifies the enclave uniquely, and it also contains ESV, Independent Software Vendor, public key hash. So when the report is signed by a trusted party, then you can verify that it is indeed the right enclave. So the party that signs this report is called the quoting enclave, and it's physically the CPU, the Intel CPU with SGX-enabled technology. So once you get this report, you can attest it using Intel attestation service. And if Intel attestation service verifies it that it is the right enclave, then you can be sure that the enclave in question was run properly and that it is valid. Why Intel attestation service is needed? Well, it is not needed. The point is that Intel has a public certificate for all these key processors. So this certificate can be used to verify signatures from all processors. And if Intel decides to publish this certificate, then anyone would be able to verify that the enclave is valid. So this is, well, it is necessary now, but it's in fact an optional step. Once Intel attestation service signs it, anyone can subsequently verify that the enclave in question is valid. So this happens only once per enclave per CPU. And we have the enclave. The requester or a challenger is sure that the enclave in question is valid. But there's one more important step, because the requester has to be able to communicate with the enclave securely. So there's one more field. The enclave can write a temporary public key into this quota, and the private key corresponding to this public key is stored inside the enclave, which makes it secure. And once it is attested, anyone can use this, well, the requester can use this public key to establish communication with the enclave. So we have the process which allows us to run the enclave. We have it on some host, but what in fact can we compute using the SGX? Well, it's a general purpose technology, but raw SGX is pretty limited in terms of what you may expect from the full-fledged computer, because the raw SGX allows you to do computations only. There is no I/O, no host connections, you cannot call DOS, so you have to statically specify I/O channels, communication channels, and, for example, threading has to be specified as well in a static way, which may be enough for some use cases, but we believe, well, we in Golem require something more because we need generic binary payloads to be able to be run inside an enclave. And this leads to Graphene. And Graphene is a library, well, it's actually a framework which contains a library which simulates operating system. So it enables us to run the arbitrary application, binary, without changing a single byte of this application inside the enclave, communicate this application with libOS, which means it's a layer simulating OS calls from the application point of view, and this enclave communicates with the host through a very well-specified platform adaptation layer, which is a very small subset of syscalls used to establish very well-specified interface between the host and the enclave. And this is very good from our perspective because it allows us to run any application. It is pretty straightforward to embed binary payload into the enclave and to run it. Of course, it requires some configuration because you have to configure SGX, for example, and establish keys. But once it's done, you just run a script and voila, it's done. But this is still one step behind what we really need in Golem because, as you know, in Golem we require Docker and containers. So we managed to do it. In fact, we cooperate with Invisible Things Labs, a company which specializes in security and at this point in Graphene. And we were capable of running Docker image inside which a Graphene with embedded Blender was run, and we were able to render pictures. So this technology works. We didn't have to change anything in the payload, in the Blender file, and we just had to tweak Docker file a bit and run script which changed this Docker file from the original one to the Graphene enhanced one, and it was ready to run with the SGX and Graphene. So, why Graphene? Well, there are three reasons for it. The first one is that from the Golem perspective, we need arbitrary payloads to be run inside this enclave. Arbitrary without any modification because we usually won't be able to modify the binaries provided by the third-party service developers, software developers. The second is we required containers. So we needed a solution which would allow us to run the payload inside the container. And the third, and maybe most important from the security perspective, is that it offers a reasonable trade-off between trusted computing base and the attack surface. Because this platform adaptation layer that you can see here consists only of 44 syscalls, which are used to communicate enclave with the host. So there are other solutions wrapping all the syscalls, which boils down to more than 350 calls, and it results in much larger attack surface, which is maybe harder to audit. So this trade-off, well, when we have small TCB, it is easy to audit the code. When you have small attack surface, it is easy to audit this interface. And this trade-off, from our perspective, looks very, very good. So we can run any payload inside the enclave, but we need to know whether it really makes sense from the efficiency standpoint. And it seems that for CPU-intensive computations, which does not require too much memory, it's a very good solution because it offers this security. The caps, and additionally, it is pretty efficient. This infographics show a hash-cache implementation inside the enclave, so the whole hashing algorithm happens inside. It does not require too much memory, which is good. And including the startup time, you can see a constant overhead between the native CPU and the enclave CPU. So in case of hashing algorithms, it might be necessary to squeeze every single piece of the CPU, but if you'd like to, for example, verify results and make sure that the results are valid, then this overhead doesn't seem very bad. But we have another class of computations, and this class is important to us, and this is computations which are memory intensive. And memory intensive computations, well, it's much worse in this case, simply because we have EPC is enclave page cache, which contains active set of pages that are allocated for the enclave. And this set is right now approximately exactly 128 megabytes, maybe larger, but it's not too much. So if you need more memory, you can expect swapping of pages, and which requires encryption and decryption, and it imposes a huge overhead on memory. So as you can see on this, those are logarithmic scales on both axes. So as you can see, this constant gap amounts to, in fact, constant percentage of overhead, which means that the ratio of time spent in enclave and in native CPU may be constant up to this point. This point is the moment where the active set is larger than the EPC. And at this point, when you have more than 128 megabytes actively used, page swapping really amounts to a huge overhead, and it may be detrimental to the computation. But still, if you would like to, for example, just verify partial results, then you can compute it in a slower way, but making sure that the results are valid. And if you need something larger, then you have to carefully choose the trade-off between the speed of this computation and the security guarantees that are provided by the technology. So what do we have from it in Golem? Because we have the enclaves, we have the Graphene, we can run Docker images, we know what's the efficiency. So it's a generic solution that may be not very efficient in specific scenarios, but from Golem perspective, it is very, very useful. So first of all, regular nodes in Golem can be used with Graphene. And regular nodes can, for example, either compute the whole result inside the enclave. It may be slower, but it's going to be valid. Or local verification may happen inside the enclave, but the computation should happen on native provider's machine, which removes burden of local verification from the requester, and it's moved to the provider. Or, for example, a few nodes, SGX nodes, can be used to slowly compute the results, and those partial results may be used for redundant verification at this point. And we have one more service, this is a consent, and the consent can use SGX nodes as its computational backend, which is guaranteed to compute the right results. And yeah, so this all looks pretty good, pretty promising, but it may be even better. So there are three possible developments or changes that may result in this technology being even more interesting. So first one is the launch enclave liberation. Right now, enclave can be run by any launch enclave, but only enclaves run by the Intel launch enclave can be run with full SGX support. Others cannot. Intel uses it, for example, to assure that there is no malware in the enclaves, but in fact it boils down to controlling which enclaves may be run or may not. So if this is liberated, then anyone can run any enclave, and this enclave will use the full SGX. Right now, if you run your enclave from your own launch enclave, you're not getting any SGX guarantees. The second one is IA, Intel Attestation Side Risk Liberation, which means that Intel publishes this root certificate for remote attestation, which boils down to attesting enclaves without this third-party IS service. And what is very important from us, but it's still wishful thinking, is secure GPU for enclaves. So if we can include the GPU inside the trusted computing base, then we have everything that we need to compute securely on both CPU and the GPU. And ultimately, we don't know if it's going to happen. Intel is working on one technology for secure display. It's not the secure GPU. It's just a secure display with hardware. But chances are that someone is going to work away towards secure GPU computations. So I'd like to thank ITL for help with this presentation, especially Joanna Rutkowska and Michał Kowalczyk, and Aleksandra Skrzypczak for help with this. And I hope that this technology and what you saw was interesting. Thank you.
Thank you. Okay, so we have about an hour break for lunch, so please go eat food, get lunch, and we'll see you back here at 2-ish.